right, guys, welcome to week 6. We are in the final weeks of this semester. I hope you guys are excited. I hope you guys have at least learned something. I know looking through the notes and the assignments and tests and that kind of stuff, I can see those things. We're getting the information out to you guys. So, with that, again, just kind of some housekeeping stuff. Again, this week is one of our last weeks that we're going to have material taught. So this week we're going through clippers and power supplies. I wanted to move the clippers in with this week because I feel they make a little bit more sense. They're really the first stage in power supplies. They are our half-wave rectifiers. Kind of with the understanding, the idea of what are these guys doing in relation to why do we need them to do it. So I shifted it back this week. This week, like I said, it's one of our last weeks of full instruction. So the plan here is we're going to cover these guys, and then we'll cover them through as much of next week as we need to. I do expect a few more questions to show up and whatnot. If I don't hear anything, then we'll just kind of continue as normal. With that being said, next week is considered dead week for ISU. So what that means is we're not going to be it really means it's another week. It's just another week, normal week. The only thing that we're not going to do is administer the final exam that week. That's kind of the idea. It's kind of a preparation for that week coming up. So that being said, we'll go through the power supplies this week. Next week we'll finish up the power supplies. Any questions you guys have, and then as we get through there, we'll do a review. And what I'll probably do is the last couple of days of the week, I'll just make sure let's try and get on with a Zoom session at least one of these times. We'll all get together and we can ask questions. We can get help from each other. Kind of see each other one final time. Through Zoom, which I know you guys have been talking and been in touch with each other throughout the semester, which is great. But let's get on one more time, and we'll take a couple of the days and go through and answer any questions you guys have for the final. The final is going to cover everything that we've covered this semester, so anything in the AC portion. Going back when we first started talking about AC capacitors and filters, reactants, we got into inductors. Then when we started getting into the filtering and we get into the AC/DC portions, all those types of things, all that stuff's going to be fair game on the test, and as well as the power supplies. And then the week after that, so in 2 weeks, I will open up the test on Monday, and you guys are free to take the final whenever you want. So once you get that final done, and you're pretty much done with theory, we do have the course evaluations if you guys wouldn't mind taking those. They're information for me on how we did. I know this one's going to be different than a lot of the classes because it's the first semester. We had the first half of the semester we were live, second half we were online, and so I understand that there's the troubles between that. Just for kind of a place for you guys to give your points, your reflections, your thoughts, things like that. So we'll go with that, and then, like I said, the week after that is finals. With as far as lab goes, make sure you get your labs done. This one will probably take a little bit longer. I've got to figure out what we're going to do for the last part of the lab. What I'll probably end up doing is having you guys. I'll give you the assignments, and you're just going to project, basically calculate how you would get that, but we're not actually going to build the last part of the lab, just because it's going to take components that you guys probably don't have. Or the easiest thing we can do too is, like we said, is for the actual measurements of that part of the lab, is try and build and design your circuit based on the components you have. And if you don't have those components, we can either get them to you or we cannot. Like I said, I haven't quite figured out how we're going to do this last part of the lab because there's so many variations because it's your guys' design based on a set of parameters. So anyways, like I said, with that being said, when we get to that part of the lab, as we get closer to the end of the week, because I don't expect anybody will be there until probably Wednesday, Thursday at the earliest, unless you just bust your labs out real quick, which if you do, that's great. I'll be thinking about what we're going to do for that part. But either way, like I said, we're coming down to the last little bit. This is the last major topics that we have, and I feel it's been a good semester. Tough, but I think it's been good. It was a good experience for me to learn how to teach all this stuff online as well, as being a new teacher with this material. So luckily I had a semester to fall back onto instead of this being my first. So there's that. So I'm grateful for it. But either way, enough said with an introduction with that. Let's get into the last couple things we need to talk about. So the first part that we have here is we're going to talk about clippers. And this is just a fancy thing for understanding how diodes work to AC signals. Now, we learned previously with diodes, what they do is, depending on if they're forward biased or reverse biased, they're either going to drop all the voltage or they're going to allow the voltage through. So depending on how it was hooked up and depending on how the orientation of the diode was. The same thing holds true when we go into AC signal. The difference being with our circuit here. So here is our circuit. Our diode is polarized like this, positive to negative, and we have, in this case, we have a 1K ohm resistor. Well, if we have a 5-volt peak signal of a sine wave coming in, and honestly it doesn't matter what the frequency is because neither of these are reactive components, as we go through, what we're going to see is we're going to graph this out. So in this orientation, when we have the first half of our wave coming through like this, so the black is our V in, over here is going to be our V out, and the green is going to be across the diode. So what we see is as our voltage in comes in, it's going to come up and it's going to peak out at 5 volts, and it's going to drop out at a negative 5 volts, just like a normal AC signal. That's what we're going to see. Well, what's going to happen is when we have this signal climbing up in our positive voltage, as it's going more and more positive till it hits the 5, what orientation and what configuration is this diode in? Is it forward biased or reverse bias? Well, we have a positive voltage going into the positive portion of the diode, so it's going to make it forward bias. So what's going to happen is when the diode is operating in forward bias, the voltage is going to come up and then it's going to flatline, because in forward bias, the voltage drop of the diode is 0.7 volts. Then the rest of that voltage is going to be transferred and it's going to be dropped across the output. So V out, and that's going to be at a peak of 4.3 volts. So they work just the exact same way as they do in DC. The diode is only going to drop 0.7 volts. The resistor, and in this case the rest of it, is going to have the rest of the signal. So at the very peak, we're going to have 4.3 volts, and it's going to follow the curve based on how the curve's going minus the 0.7 across the diode. The difference is, now that we go through, now we have a positive iteration, now we have a negative iteration. So we can see both of these happening without having to switch our diode. So what we do now is we start getting into the negative voltage. Well, when we start running a negative voltage up through here, so now we're running the negative half of the sine wave through. Now we come up here, we hit the positive side of the diode, which in turn reverse biases this diode, means the diode is going to drop all the voltage across himself. And the resistor is going to have none. So that's what our waveforms are going to look like. Our output is only going to see the positive portion of the diode, of the waveform. The negative is going to all be dropped across here, so in a sense, we have clipped or eliminated this half of the sine wave on our output. The voltage is still there, but it's not where we want it. So the whole idea behind this is to kind of break this out a little bit, so they're all stacked together. So if we have a sine wave that looks like this coming in, and I'll do a couple of iterations, our output is going to look like this. So what this has done effectively is it's removed half of the signal. Now we've gotten into what we're going to call a half-wave rectifier here in the next little section. But just the same way as it worked in DC, it's going to block current going in the opposite direction of how the diode is. So if we had flipped this diode around and gone like this, now in the positive portion of the waveform, so we draw this waveform right here. So this is our V in. So now when the positive portion of the waveform comes and hits, we're going to be reverse bias. So we're going to drop all the voltage across the diode. So all of our V out is going to be 0. The V diode is going to drop all of the positive voltage. And then when it goes into reverse bias, and when the negative portion hits, then we hit the negative portion of the diode, so then it's going to be in forward bias and turn on and allow it to conduct. And so what we're going to see is this. And this right here is our 0.7 volts across the diode. And then our output on the negative slope is going to follow the curve minus the voltage of the diode. So in this instance, what we end up with is the two waveforms. So here's our V in and our V out. So in this case, we allow the negative portion of the wave to go through. So that's kind of the cool things that we have with these clipper circuits is it's all based on the orientation of the diode, which half of the waveform it's going to take care of. And so is it going to, and the whole idea is to look at it. Is it going to be a forward bias diode or a reverse bias diode? And remember the rules of how they work. If it's forward biased, it's going to turn on and it's only going to drop 0.7 volts, allow everything else through. If it's in reverse bias, it's going to basically act as an open. It's going to break the circuit and everything's going to be dropped across it. And so the one way that we calculate this, so like in the homework, so the homework, that homework assignment is, I'll move it to week 6. It's still going to be worth part of your final grade, but it was just not required for to unlock the test. But like I said, I'll get it moved into this week so remember to do it. So the idea behind this is now we have a circuit and we want to be able to solve for what the outputs are at specific points on the waveform. So for example, using this circuit in a practical application, what we are doing is we're just basically constructing what the output is going to look like. So in this case, here's our diode, here's our resistor, and it honestly doesn't matter what the value of our resistor is, we'll just throw a 1K ohm in there for fun, and we have 16 volts peak. So what we have to do is at each of these waveforms, we have to kind of determine what is my diode in? Is it forward bias or reverse bias? That's our step number 1, okay? So remember that when we are looking at a waveform, when we start, we're at 0 degrees. When we hit our first peak, that's 90 degrees. When we come back to the center line, it's 180 degrees. When we come back here, we're at 270 on the negative end. And then when we come back up to 0, we've gone full way around, so it's 360 degrees. So we've gone through the full circle, the full rotation. So now what we have to look at is, okay, what is the question wanting? What points do we want to check our voltages? So I'll write out this list of them and we'll go through and solve them real quick. And then we'll also do it, so we'll do it once like this, and then the second time we'll do it where we reverse bias the diode, or not reverse, we reverse the polarity and the position of the diode. And then we'll solve for that, and it will, using the same value, same point, so we can kind of compare against them. So the values we're going to look at is we want to look at the voltage of R1 at 35 degrees. We want to look at the voltage of diode 1 at 35 degrees. So the same point in time for both the components. We're going to look at the voltage across R1 at 90 degrees, the voltage of the diode at 90 degrees, the voltage of R1 at 152 degrees, the voltage of the diode at the same point, 152 degrees, the voltage of R1 at 180 degrees, the voltage of the diode at 180 degrees, and then finally the voltage of the resistor at, sorry, not finally, 270, voltage of the diode at 270, and then finally the voltage of R1 when we get back to 310 degrees, and then the voltage of the diode at the same location. So the reason why we're doing 2 of these is we want to find out what the voltage drops across both sides are. Okay, so let's take a look at our first one. So 35 degrees. So we come back and we look at our chart. 35 degrees. Okay, it's probably going to be right about here. Okay, give or take a little bit. So we're just going to call this one 35 degrees. So when we're at 35 degrees, we're in the positive peak of our waveform. So that means we have positive voltage coming through, coming into the positive portion of the diode, which is going to make the diode forward bias. So which means the diode's going to turn on. And then at that point, the voltage is going to be 0.7 volts if it's high enough to support that, like if our total voltage. So then we have to look at what is the total voltage of this guy. Because at 90 degrees, our V in is going to be equal to 16 volts. But what is our max voltage at 35 degrees? Where are we at on this scale? So the way we do that is we've already looked at this formula before. So our V out, or basically our voltage, is going to be the amplitude, so the max amplitude that we have, times the sine of theta. So whatever theta is, we're going to plug it in for there. And this is going to give us the maximum amount of voltage we could have. So at 35 degrees, our Vmax, and I'll just kind of write this in between. So Vmax is equal to amplitude, so the max amplitude, so it's 16 volts, that's the highest we're ever going to get, times the sine of theta, which is 35. We plug that into our calculator, and that spits out 9.177. So the most amount of voltage we're going to have in the circuit right at this point in time is 9.2 volts, essentially. Okay, so we got 9.177 volts. So now we have to look. Do we have enough for the 0.7 drop across the diode? Yep, and that's all it's going to take. So the diode at this point is 0.7 volts. That's all it's going to have because it's forward bias. Okay, so then if we have a total of 9.177 volts, we're dropping the 0.7 across the diode. The rest of it has to drop across our resistor. So across that guy, we end up with a total of 8.477 volts. Okay, so that one was pretty easy. Now we're going to come back and we're going to look at the next one. So when we're at 90 degrees, so when we come here at 90 degrees, the maximum voltage is going to be hit. So our Vmax is equal to 16 volts. Now we have to, so now that we know that we have enough voltage, we're still in the positive region of our input waveform, which means the diode is still forward bias. And if the diode is still forward bias and we have the voltage to support it, it's going to be a 0.7 volts. And the VR1 is going to be what's left over, so 15.3 volts. Then we want to look at 152 volts. So we come over here, 152, it's, coming around here, or sorry, 152 degrees, not 152 volts. So 152 volts, so we're still positive, so we're still forward bias, so we're still going to be dropping 0.7 if we have that ability. So now we want to find out what our max is at this point in time. So our Vmax is equal to 16, because that's the max voltage we could ever get, times the sine of 152 degrees. And that gives us a value of 7.512 volts, which we can check. That's a lot more than the 0.7 that we need. So our diode is going to be maintaining its 0.7 volts. And what's left is going to be the 6.812 volts being dropped across our resistor. So now that we have that value, we can go to the next one. Now we're going to look at 180 degrees. Well, at 180 degrees, it has just gotten back to 0 volts. So we're back at the line and it's getting ready to switch into the negative iteration. So if there's no voltage, there's going to be no voltage drop across the resistor and no voltage drop across the diode. There's nothing to distribute between the two of them, so that one's an easy one. 270 is our next value, so we're going to look here. So at 270 degrees, we're at the peak of the negative part of the negative iteration of our sine wave. So our max voltage here is going to be a negative 16 volts. And then we look, okay, we're in the negative iteration, so that means we're sending a negative pulse now this direction into the diode. Well, the negative is going to come in contact with the positive portion of the diode first, which means it's going to reverse bias the diode. So the diode is going to shut off and it's going to open up, and it's not going to allow any of the AC voltage through. So the diode, now being an open, is going to drop all negative 16 volts across it. And what's left across the resistor? 0, because there is no current flow to that device. That diode is stopping it at that point. So then the last one we have is 310 degrees. So again, we look at our original waveform. So 310 is probably going to be sitting right about here. And we're still in the negative iteration. So we know at this point the negative iteration is there. The diode is going to be reverse biased because of that. So the diode is going to drop everything that it has. The resistor is going to get nothing. So we can fill that out right now. The resistor is going to have 0 volts. And the diode is going to drop our Vmax. And this time we need to calculate what the Vmax is. So again, it's 16 times the sine of our angle, which is 310. And when we do that, that gives us negative 12.257 volts. And so since the resistor is dropping nothing, the diode's open, it's going to drop all 12.3 volts across it. So that's how that one works when it's in forward bias. Now let's take a real quick look at what happens when we flip this diode and we put it into our reverse bias. Okay, so now we're going to look back at these same values. So the Vmax is not going to change because we haven't changed our input at all. We haven't changed the voltage settings or anything like that, the resistors. All we've done is flip the direction of the diode. So this Vmax is still going to be the same. So here we're gonna go with, so this is going to be D1, and then the purple is going to be D2. And all we've done is flip direction of the diode. That's the whole idea. So D2 is going to reverse the bias. So that means when we come up to this point, we're going to have a 9.17 volts positive because we're right here. When we come into the positive, it's going to hit to the negative of the diode first, which is going to reverse bias the diode, which in turn is going to cause it to basically be an open, and it's going to drop all the voltage. So at this point, the voltage across the resistor is 0 volts because there's nothing getting through, and this is going to drop all 9.177 volts. Then let's look at the next one. So when we're at 90 degrees, we're at a maximum of positive 16. So again, we have a positive voltage going into the negative of the diode. So the diode's going to act as an open. So the voltage across the resistor is going to be 0, and the voltage across the diode is going to be the full 16. When we shift to 152 degrees, right here, we're still in the positive iteration, which means our diode is still going to be reverse bias. So our resistance voltage is going to be 0, and the max voltage, the voltage across the diode is going to be the max. So then we have the 7.512 volts. Then when we come back to 0, it's going to stay the same because, again, we don't have any voltage drop because there's no voltage input. Then we come back down to 270. So now we're in the negative iteration. So we have a negative signal going into the negative part of the diode, which is going to turn the diode on. So when the diode is on, it's going to drop 0.7 volts. And we know we have negative 16, so we're covered with that. So the diode is going to drop at negative 0.7 volts, and then the resistor is going to drop the negative 15.3 volts. Then on the last portion, when we come down here to 310, so we're right here again, we have a max of negative 12.257, which is more than enough to maintain the negative 0.7 volts that it's looking for because we're in the negative section. So the diode, again, is going to be dropping a negative 0.7 volts, and our resistor is going to be dropping the rest, and that's going to give us 11.557 volts. So real quickly, we can kind of show and demonstrate, okay, this is what's happening. When the diode is reverse bias, it's going to clip off that portion of the waveform and not allow anything through. When it's forward bias, it's going to allow it through, minus the voltage drop across the one diode. So with this, so like I said, when we come back here to these waveforms up here, in the very beginning of these slides up here, this is what we're looking for. So this is called, like I said, this is called a half wave rectifier because it's clipping off the negative portions of the waveforms. Now we can use that to now create a AC signal. So one of the things that we're going to look at is, like I said, kind of moving forward a little bit with the understanding of why we want the clippers. That's really all there is to the clippers. Um, we don't have much else to talk about that. So, but the thing is it clips off portions of the waveforms, and then we're going to use that. So how do we use that? Well, when we're looking at our waveforms, coming into our output, we have this waveform looking for us. So we have this positive, then it goes to 0. We have another positive hump, and it goes to 0, and then that's what we're looking for. Well, in a power supply, we want the DC voltage. So in an AC waveform, when we have a positive and negative slope, our average is 0 volts, the true average of this guy. But what we're going to be looking at is, because now we've eliminated this section of the waveform, we've clipped it off, what we need to know is what is the average of the waveform from the beginning of the wave to this part of the wave when that part's 0 and we have here. So what we have in this part is we have another value that we're going to use, and this is a value that we're going to calculate in calculus. So the average of this waveform is 0.637. So I know before we've been using the 0.707, and like I said, we'll when we get into the calculus portion in third semester, you guys will have a better understanding of where these values are coming from. It has to do with the areas under the curve, the slopes, all that kind of stuff. And so, like I said, you'll get to that point. But for right now, just understand that this is the average of the wave of a sine wave. Of a sine wave for just part of the like one iteration, either the positive or the negative iteration. So now that we have those, what this is now is that then becomes our DC value. So the things we're going to be looking for in these power supplies is we have to know a couple of values to do it. We have to know the maximum value that our sine wave gets to and the minimum value that our sine wave gets to. So in this case, the V max is going to be whatever voltage we have peak, and V minimum is going to be 0. Because that's where it's trying to get to, because that's how the waveform is going to get. And that comes important when we start talking about the filtering. So we have these two values. Now what we do is we're looking for our VDC is going to be the average of these values. So if we look at it, we can kind of break this guy into two parts. So we've got part 1 and part 2 over here. So to calculate, so the average, like I said, this is where this 0.637 comes from. So the VDC is the average, average of waveform. Okay, so we have to factor in these two parts. So we take the average of the first part, which is the 0.637, multiplied by our volts peak, and we're going to add that to the average of the second part, which in this case, it's 0. So that makes it really easy for us. And then again, to solve for the average, is we take the two values, or the values we're looking for, we add them all together, and then we divide it by the number of values that we're looking at. So in this case, we have two values. So we're going to divide this value and or add these two values together, because we broke it up into two parts, make it simple, and divide it by 2. That's going to give us the average, or our DC value of this guy. So there's our final equation for this. So V peak times 0.637 divided by 2. Because with that 0, it's not going to do anything. We can just simplify it down, and this is where we get to. Now, we're going to use this formula only in one circumstance. Because we have this section of our waveform right here that goes to 0, this is when we're going to use this formula. We have another formula that we're going to use once we get to where we don't actually reach 0 anymore, when we start, delaying it out, filtering it out, the ripple, as we call it. We're filtering out the AC portion to give us a really tight DC value. Now, the whole idea behind these, and one of the understandings is we're trying to get we're trying to get a specific voltage out with as little AC as possible. And so as we go through these, I'll show you guys through the iterations of how these, how we can build them. We'll start off with some unfiltered ones. We'll get into filters, things like that, and you guys will see that as we get better and better, we start getting to the point where we have almost no AC coming out, and it's all pure DC, which is the idea of power supplies. Because if you were to take your power supply from like your phone, for example, which you could do since you have your scopes there, just take your USB cable coming out. You can find the pins, connect into them. Be careful that you don't short them out. Or you can get one of like for a laptop that has the barrel plug that you can touch the outside and then one probe goes on the inside and then you can actually see your voltage and you'll see it. And then if you zoom in, if you take your volts per division and you zoom that in a crap ton, and then, if you have to change your time to see it, but what you'll actually see is that DC line is not flat. It is actually has a signal on it, and you can actually measure that. And that's what we're going to be doing with these guys. And that's where this comes from, this DC value that you're calculating. That's what the rating of your power supply is, and that's how it's calculated with this kind. So like I said, there's different kinds and different types that we're going to talk about, but this is why this value is important. This is the output setting. This is what we want to get with the power supplies. So when they're unfiltered, we're going to use this formula to calculate for them. After that, some of the other values that we need to know. So this is going to give us our Vmax, our Vmin. We have our VDC, which is one of the primary values we want. Then the next one we have, it's the voltage ripple. And that's going to be our Vmax minus the Vminimum. And that's going to give us a value in peak to peak of our AC signal. And this is important because this is how much our DC voltage is going to be changing. So like with this half-wave rectifier, we're going to see it go up to the value and then drop down to 0, but that's going to give us an average DC value across the whole thing. So we're not just looking at one iteration, we're looking at multiple times. And so this is another one we get. And then the last thing that we need, so we have our ripple, which is our AC portion of the circuit. So we're getting back into last week where we have an AC signal and a DC signal. The AC signal is going to be riding on a DC voltage, which is what we're doing here, because now that we've clipped this off, instead of the DC signal being 0, it's going to move it up because it's not driving it so far negative. It's not getting rid of it. And like I said, this is all stuff you guys will measure and see in class. And feel free to ask me questions. I know this is going to be kind of a little difficult section, but like I said, ask questions, let me know, hit me up through text if you need to, or we can get on a Zoom, we can talk face to face and kind of draw things out. Zoom, I think, is a little bit easier for explaining things when you guys have questions because I can draw pictures, you can draw pictures, and we can directly interact with each other, where text is a little bit harder to do so. But like I said, if you do have questions, please let me know. So we have our V ripple, which is important because that's our AC portion. But the last key thing that we want is our percent ripple. And what this is the rating. This is the efficiency of our power supply. So we want to be able to have a very stable power supply. So we want our percent ripple to be as low as we can get it. But again, you also have to take into consideration costs. And I know, like I said, I know you guys are probably sick of that, but that's one of the biggest things is what can I get away with for the cheapest amount? And that's where it comes down to. So our percent ripple is the other big factor. And this is where you're going to pay the money for a power supply. So if you're looking at 3 power supplies to purchase for a project, one of them's $15, one of them's $10, one of them's $5. When you're looking at them, you're like, okay, which one do I need to use? Well, you have to consider a couple of things. What's your budget? So for every computer we ship out, we have to send a power supply with it. Am I going to send the $15 power supply? Am I going to send the $10 power supply, the $5 power supply? If you looked at it straight from a business standpoint to where it was all about dollars and cents, you would send the $5 power supply every single time. But the problem with that is it's missing some components that we used for further filtering and things like that. But it has a very high ripple, so which means the voltage is going to be changing. And so if you have at one point, you could go from like say it's a 15 volt power supply, and our ripple is sitting at 100%, just for an example. Which that means that 15 volts is changing plus and minus 15 volts every time. So at some point in the wave, and some point in its operation, it's going to be seeing 30 volts, and the other time it's going to be seeing 0 volts. And so if you don't have components in there that can handle the 30 volts, you're going to get stuff that burns up. Plus, some things don't like having that big of a fluctuation. When you start getting into digital, that much fluctuation, a 15 volt swing, is going to kill any kind of digital signal you have, because there's a range that the ones and zeros can be in. And you guys, like I said, you guys will get that into there earlier, but that's the idea behind this: is we want a very stable, very small ripple value for our voltage. So these are kind of our two keys, the VDC and the ripple. And the way we calculate the ripple is we take our V ripple in peak to peak. We have to, let's see, let me rewrite that because that's just a bunch of gibberish. We take our V ripple, we have to convert that from peak to peak into, so peak to peak into RMS, because we want to be able to compare how much change in voltage is going on. And so our VDC, remember, is equivalent to the VRMS of the power supply. So we want to make sure that we're comparing, again, apples to apples, and we want to be comparing the exact same kind of apple to the exact same kind of apple type of a thing. So we're converting them into the equivalents. And so the way we do that is we have our voltage ripple in peak to peak. So we have to divide that by 2 to give us our voltage ripple in peak. Then we have to convert that into RMS. And so then the way we do that is we take our V ripple in peak, we divide it by the square root of 2, which in this case, remember, this is our magic 0.707 value. So we divide it by that value, and that's going to give us our total conversion into V ripple in RMS. So now we can compare them. Then to find the percent ripple, that is equal to the V ripple in RMS divided by our VDC. So basically, how much change are we going to have? We multiply that by 100. So like I said, once we start throwing some numbers in there, they'll start making sense what these are going on. And then as you start measuring them in lab, these concepts will start making sense. You'll be like, oh, I see the ripple voltage coming out on this thing. I see my DC value. I see, these different things. And so when we finally get to the point where we have, we're filtered out, we're less than 1% ripple, you're going to hook up your scope, you're going to see it, and you're like, oh, look, there's my DC line. I'm riding right at 25 volts. But now I need to look at my ripple. So you turn this, so you have DC coupling, then you'll turn it to AC coupling, and then you're going to look at just this little wave that's going to be centering, like, oh, I've got 100 millivolts peak to peak on this guy. So I've got a really good signal. But anyway, like I said, that's where we're going to get to. And so I just want to make sure you guys, understand the basis of where these formulas come from, and understand how they're going to work. We will make a couple of changes as we go, but these are the very base formulas that we're going to look at. And like I said, I'll show you where we change them. So the idea behind this is we have 3 styles of power supplies. We have the half wave, we have the full wave, and we have a full wave bridge rectifier. So we have a half wave rectifier, a full wave rectifier, and so I'm going to erase this right here. So we have 3 rectifiers, half wave, full wave, and a full wave bridge. And then we have 3 types of those power supplies. So we're going to cover 9 different styles of power supplies. And like I said, it seems a lot, but we're going to solve them all, and then we're going to chart them and graph them, and we'll show you guys the difference between them, the pros and cons of each of these guys. So the 3 types that we have unfiltered, we have filtered, and we have pi filtered. And we'll talk about the reason why it's called pi. And obviously these are going to go from in order of efficiency. So the worst is going to be unfiltered, the best is going to be pi filtered, the worst power supply is going to be the half wave, and the best power supply is going to be a full wave. So that's kind of the prelude to what we're going to be doing with undering it. So like I said, the clippers are going to come into place because we're going to clip them, but then we're going to be pretty much using those same values. So we're not going to talk about clippers again, but I just want you guys to understand at least the basics of how the clippers worked. All right, now that we've got this out of the way, let's get started with some actual understanding of what power supplies we want to look at. Okay, so the first one we want to do is we're going to look at our unfiltered power supplies, and we're going to go through the whole gambit of them. So unfiltered power supplies. These guys are the cheapest, they're the easiest to build, they're the easiest to calculate, but they are very, very, very inefficient. You're going to see massive changes in your voltages coming out, which could cause problems for other components later on. All right, so our schematic for an unfiltered power supply is going to look like this. This is going to be taking into account now we're going to be using our transformer a lot. So the idea here is we're going to be taking 120 volts and we're going to be creating a power supply of some voltage. So basically what we do is we're going to plug this guy into 120 volts at 60 hertz, plugging it right into the wall. It's going to come into our transformer. It's going to come out of our transformer. And then what we're going to do is we're going to go through one diode, and then our resistor, and then we have our ground right here on the secondary. So one of the things about this is we're using this transformer to completely isolate ourselves from our primary. So this circuit over here, this power supply, has no physical connection whatsoever to the circuit that we're plugging into the wall. So you have to remember that. This ground right here is very important. Everything has to connect to that on this side of the circuit, and we don't want anything to cross over. It will mess up measurements, and it will do some funky things, and could potentially, cause you guys some damage. So please remember that. We are dealing with 120 AC. This is coming straight out of the wall. Be very, very careful with that. So when we look at this, one of the things we have to remember is what is our transformer. So most of the ones that we have, you guys might have a 5-to-1 or just slightly different, but you guys have already gone through the measurements on your transformer. You figured out what it is, how much voltage in to how much voltage you get out. You're going to use that same number in these calculations. I'm just going to use a 4-to-1 because it makes life a little bit easier. So now the first things that we got to do is when we come to this power supply is what the heck is going on with the circuit. So we have to go through and analyze it. The first thing that we need to look for is when we're solving these types of circuits, because we want to be able to see them on our scope. Well, the easiest place to kind of track numbers is we want voltages to be in peak. So voltages should be in peak to view for our calculations and everything, because on a scope you have the peak, you can throw it over there, you can tell your cursors, your measure menus, whatever, give me the max value, set for the max value. That's quick and easy to find. You don't have to worry about timing or anything like that. What is just my maximum voltage that I'm going to be reading at these points? Okay, so in this case, remember what I've said before on some of the assumptions we have to make. If on our power supply we are not told if it's peak to peak, peak, or RMS, we assume that it's meaning it's an RMS. So that's how our multimeters work. If you put them to AC and plug them in, you're going to read 120 volts RMS, not peak. That's the big difference between scopes and DMMs. The scopes will give you the whole waveform and measure any points, including the peaks. The DMMs only give you values in RMS, which can be deceiving if you're not ready for it. So with that being the case, so if we have 120 volts, and remember the RMS is equivalent to DC, so we have 120 volt DC coming out. That's kind of the idea behind this. But now we want to clean the signal up to where we have just 120 volts and we're not fluctuating very much. So with this being here how it is, so we have 120 volts, there's nothing given, so that's RMS. We need to get this guy into volts peak because volts peak is just easier to work with. And plus that's what we can read on the scope. So to convert volts peak, remember our VRMS is equal to the volt peak times 0.707. We've done this calculation plenty of times before. So we're just going to switch this around. We're going to divide both sides by the 0.707. And we're left with volts peak is equal to the VRMS divided by the 0.707. And that will convert this back and forth. So the first thing we need to do is we take 120 volts RMS, we divide that by 0.707, and that is going to give us 169.7 volts peak. So if you were to hook up your scope up to the 120 volts coming into in from your transformer, this is what you're going to see is basically 170 volts peak coming in. That's where that waveform is, and that's where the 120 comes from. So now when we measure under scope, we can real quickly, I have 169, I'm good. So now at this point in our waveform, we have 169.7 volts peak, and I'm going to label this as point A. So our primary coming in from the wall before we've gone through the transformer, we should be seeing 169.7 volts peak. Now I wouldn't suggest, hooking these scopes that we have up to that value. I don't know if they can handle or not. I think it's right on its upper limit if it hasn't crossed it. But I mean, look in your manuals again and double check. But anytime you're using test equipment, make sure it can handle it before you just plug into it. The DMMs will read it just fine. The scopes we have in the lab will read it just fine. I just can't remember if these ones will or not. I've got to look in the manual again, but you guys also have copies of the manuals. So just know what your scope can handle, because if it can't handle it, don't do it. You'll burn it up. Okay, so after we've analyzed the circuit, we have 169.7 coming into our primary. It's going to go through a transformer, and we're going to convert it to a secondary value. So a 4-to-1 ratio means that we have 4 times as many coils on the primary as we do as the secondary, so which means this is going to drop the voltage down by 4 steps. So at point B, the voltage of our secondary is equal to the voltage of the primary divided by 4, because that's the turns ratio. If you have 4.2, use the 4.2. Whatever you've calculated previously for your transformer, go ahead and use that value to continue with it. So what we have here is we have 169.7 volts peak divided by 4. That's going to give us 42.45 volts. So it stepped it down quite a bit, and this is a lot safer to use. It's still quite a lot of voltage, but 42 volts peak versus 169 volts peak it's just a lot better to work with. You don't have to be quite nearly as cautious that you're going to get electrocuted. It still still hurt, but you have less of a chance to do it. Lower voltages means a bigger distance that it can arc, that kind of stuff. Anyway, I mean the farther away you are, the safer you are. It has a smaller distance. You have to get really, really close to get it to arc, so less chance for mistakes. Okay, so the idea here is now at point B, we have 42.425 volts coming into the circuit. So right now we're pretty much done with the primary. The primary is always going to stay the same because we're plugging into 120 volts in the wall. So anytime we do our calculations, we can know that everything up to that point, up to the primary and even into our secondary, we know what the full secondary is going to be. Now we're just going to, manipulate it a little bit. So we have this voltage coming in. So now what we're looking at is after we've gone through here, we're going to run through this diode, and we're going to come back over here to point C. So one way to look at it is before the diode, after the diode. So this first part, this is our primary, this is the plug, this is our isolation transformer. This is, so I'll label it here in green. This is our rectifier. And then we have our load. So like I said, we're not doing any filtering right now. So one of the things we need to look at is we want to be able to find what our VDC is and our percent ripple. That's the end game of all these guys. So the big question is, what is our VDC and our percent ripple? Okay, so after we've come through the diode, and one of the things we'll look at is the different waveforms. So at point A, we have our signal coming in, and it looks like this, with 169.7 volts peak. At point B, after we've gone through the transformer, we still have our sine wave, but now we're only at 42.425 volts. And then at point C, basically what we're going to have is this. And then this is going to be the, well, that's what we're gonna calculate. What are these values going to be? And then here, this is our VDC. From here to here, that's our V ripple. So how much is the output changing across our DC line? So now we've shifted it from being a 0 DC volt up to this average. So now what we need to do is we need to find these values. And since we're dealing with no filtering, we're going to use this first set of equations. So to solve for this, our VDC is equal to the voltage peak, or I guess I should say the voltage of the secondary minus the voltage drop of the diode. And then that value, let me back up just a little bit. I'm getting ahead of myself. VDC is equal to the Vmax times 0.637 divided by 2. That's our formula coming in. So we need to find out what the maximum of our output is. We need to find out what the minimum of our output is, and we can solve the rest of these. So our VDC is this value. Our V ripple is equal to the Vmax minus Vmin, and then, like I said, we'll get to the percent here in just a second. So our max at point C, remember this is all at point C because that's our output. The max voltage is going to be this max value of the secondary minus the voltage drops of the diode. So there's only one diode drop, so that's going to take away 0.7 volts. So what's left is equal to V secondary minus the voltage drop of diode 1. So we have 42.425 volts in peak minus 0.7 volts in peak. So our Vmax is going to equal 41.733 volts in peak. The minimum is what value is this going to drop down to? Well, in this case, it's going to come up and then it's going to completely get to 0, then it's going to stay 0, then it's going to climb up again. So the minimum voltage is going to be 0 because it's going to get back down to this line. When we filter it, that's not the case, but like I said, we're going to get there. So now we have our max and we have our min. Now we can calculate the important values. So now we're going to take our VDC on the output. So the Vmax is 41.733 volts peak. We're going to multiply that by the 0.637 because this is going to convert our peak voltage to the average of that section, and we're going to divide it by 2 because we have to take into account the whole waveform. So we have one iteration, this whole waveform. So this is our V peak times 0.607 or 637. This part is going to be 0 because there's no change. We're going to divide that by 2 because we're taking the average. So the VDC we get after going through that is going to give us The first port is, so if you take the 41.637, that's going to give us 26.579 volts. Divide that by 2. So the voltage we get out DC is 13.289 volts. So if we were to build the circuit, hook it up with our DMM, we set it for DC voltage, because that's what we're interested in, we would measure 13.289 volts. Now, the problem is when we look at it on the scope, we're going to be seeing the 13.289 volts, but this thing's going to have a huge peak or huge ripple. It's going to be changing all the time. So we need to find that value. So the V ripple in peak to peak is V max minus the V minimum. So V ripple peak to peak is equal to the 41.733, the highest it can go, subtract the lowest it can go, the difference of the two, which is 0. So our V ripple is equal to 41.733 volts. So that means this signal is going to be changing, 13.289 volts is going to be changing by this much total. So top and bottom is going to be the total change. Now we can take that and we could solve for that. So if we took this guy and we divided it by 2, as a point here. So if we take this value, divide it by 2, because we want to convert to peak, we're going to get 20.867 volts peak. So what this means is this power supply, if we were to look at it and we wanted to represent it graphically, it would be 13.289 volts plus or minus this value. So we're going to see this thing climb, 13 is going to be the average. It's going to climb up to the 41.7. And we're going to see it drop down to the negative. So that's all we're doing is we're just showing this in different ways. This is just a way to kind of double check so what we're seeing on the scope is what we're seeing. But this is how bad it's going to be. Like we're changing 20 volts up and down. So we go from 13, we go up to 43, we go down to 0. Because at that point we don't have any more voltage to go. So this is how bad it's going to get. And then, so we need to do our percent ripple. Because again, this is the other value that we care about. We want to know how much is this thing going to vary or could vary from our set point. So remember the formula for our percent ripple for an unfiltered circuit is equal to the V ripple in peak to peak divided by the 2 root 2. So really we've kind of already done this divide by 2 step right here for this value, just to kind of have an idea of what it's going to, what our output waveform is going to look like. But we can throw it all together in one formula and solve it all. And then this is going to be divided by our VDC multiplied by 100. Because we want to see how much is it's going to vary from our DC set point. So we plug these values in. So the percent ripple is equal to the 41.733 divided by 2 root 2. We divide that by our VDC, which is 13.289. Then we take that whole value and multiply it by 100. The percent ripple we come up with at the very end is 111.032%. So we're varying 100% of our power. So which means we're never locked in on that step, and we're overshooting both directions. This is horrible. Okay. Think of like if we're trying to get think of all the frustrations you guys have had, using these scopes and these generators, for example, trying to get them to lock into a value. They fluctuate a little bit. And if you got something that's fluctuating 111% of your set point, it's going to be double that value, and it's going to be none of that value. So you're going up and down. And so it's very, very inaccurate to do that. But this is a power supply. We are providing a 13.2 volt signal, but I mean with these two values right here, this is going to be a cheap power supply. A lot of times, for an example, these are the power supplies you guys buy from the dollar store or, from the low end stores, the ones that don't cost very much money or the ones you get on Wish. This is the type of power supply it's going to be, because, if you plug it in, it's like, oh, this is a slow charger. That's because there's a very low voltage coming to it with a high ripple voltage. It's not going to be very good at charging components. It's not going to be very good at powering components. It is not efficient at all for what it's trying to do. So, kind of a word to the wise on that one is understand that yes, we can do this, but there's times where we need quality over the quantity. It needs to be a good, clean, crisp, clear signal, especially for testing. And you guys have seen that both when we were in school and doing labs at home. If things are varying on you, it's really hard to calculate and get things correct. So anyway, so that's kind of the first walkthrough of an unfiltered half wave power supply. So what I'm going to do here is I'm going to go ahead and end this video because it is getting a little long. I'm just over an hour right now, and I don't want to go too much farther. But the next video I have, I'm going to be going over the full wave rectifier that's unfiltered. I'm going to be going over the bridge full wave unfiltered circuit, and then we'll get into the next. And then after that, we'll start building our graph to kind of compare all these different possibilities that we have. Because remember, we have half wave, full wave, and a bridge, and we have unfiltered, filtered, and pi. And then we can kind of see, okay, what type do I need? When you get a power supply, you're going to be given a parameter of voltage to get to and a ripple voltage to get to. And so those are your two parameters that you're going to design your circuit. And so you can kind of see, oh, I don't need that high of a voltage. I can get away with using this style of them. For example, for the full wave versus the bridge, you're going to get about half the voltage coming out of a full wave, and then the bridge, you're going to get double the voltage coming out for about the same accuracy, the same variation. Again, it just comes at the cost of components and things like that, and that could be what you're asked for. I have a list of power supplies that we did last year, and I'm just going to reuse those lists and assign people values to calculate those for at the very least. But that's the idea: is you're going to design me a circuit to fill those parameters. And I don't care. There's a lot of times I don't care what your ripple is. I just want a DC voltage of this much. If you can get better than that, great. Other times there's one like, okay, I want this power supply at this voltage, but I want this much ripple, very middle. So then you can kind of look and compare and choose which one can I do, which one can I get away with, what's going to meet that, I'm designing something to meet my customers' demands. How can I do that? And so that's kind of the idea, is we're teaching you guys the skills of how to build these things, not just understanding them. And I hope that, I'm getting that message through. But anyway, this was an unfiltered half wave power supply. So again, if you need to go back through, watch the video again. If there was some issues that you guys have or you have questions, please feel free to reach out and let me know. I want to make sure you guys get this information.